Hello everyone. Today we will present information about the control of robotic manipulators using PWM signals. In particular, I will focus on the PIC16F877A microcontroller, its CCP module, and the generation of PWM signals. So this presentation will begin with an introduction to the PIC16F877A microcontroller employed in this study. Subsequently, we will discuss the CCP model of the PIC16F877A, which will be used to generate PWM signals. Thereafter, we will elaborate on the process of generating a PWM signal with the PIC16F877A. We will address the robot manipulator to be used in the study and highlight its technical specifications. Finally, we will experimentally implement the control of the robot manipulator using a PIC16F877A. So, what is PIC? PIC stands for Peripheral Interface Controller and was developed by the company Microchip. Since it is a microcontroller, it includes many hardware units within a single chip, such as CPU, RAM, ROM, ADC, timers, counters, and input-output ports. This allows us to perform complex applications using only one chip. The main reason for its popularity in robotic applications is that it is low cost and easy to program. The figure here shows the block diagram of the PIC16F877A. On the right hand side, we can see the input-output ports. The PIC16F877A has a total of 5 ports labeled A, B, C, D, and E. In addition, the diagram also shows the program memory unit, timer, and counter modules, as well as the CCP and analog digital converter modules. This block diagram shows the internal structure of the PIC16F877A. Inside, we can see the processor unit, memory units, input-output ports, the ADC, serial communication modules, and the timer units. This architecture allows us to design systems without requiring many additional external components. This PIC has 368 bytes of data memory, 3 timers, and 8 analog inputs. It also provides a total of 5 input-output ports labeled A, B, C, D, and E. Further specifications of the device, such as program memory size, EEPROM capacity, and peripheral features, can also be seen in the table shown on this slide. The PIC16F877A contains 2 CCP modules called CCP1 and CCP2. CCP stands for Capture, Compare, and Pulse Width Modulation, which are the 3 operating modes of this module. In Capture mode, the timing of external events can be recorded. In Compare mode, outputs can be generated at specific in Compare mode, outputs can be generated at specific time intervals, and in PWM mode, Pulse Width Modulation, signals are generated which are widely used for motor control. Since the focus of this study is on PWM signals, we will move directly to the PWM module without going into the details of the capture and compare modules. In PWM mode, the CCP module generates a signal with a duty cycle on the selected output pin. The period and the frequency of this signal are determined by the timer 2 module. The PIC 16F877A provides two PWM output pins, RC1 for CCP2 and RC2 for CCP1. The characteristics of the PWM signals are defined by the three parameters: the oscillator frequency of the microcontroller, the PR2 register value of timer 2, and the prescriber value. In the following slides, we will also see code examples written in the CCSC language. In this slide, the PWM period is calculated as follows. The T PWM equals T command multiplied by the timer 2 prescaler and multiplied by PR2 plus 1. Here, T command equals 1 divided by F command, and F command is equal to the oscillator frequency divided by 4. Finally, the PWM frequency is calculated as 1 divided by T PWM. In other words, the PWM frequency directly depends on the oscillator frequency, the timer 2 settings, and PR2 value. In this slide, this waveform shows the PWM signal. The most important concept here is the duty cycle. The duty cycle is the ratio of the time the signal stays high to the total period. When the duty cycle increases, the motor rotates faster, and when it decreases, the motor slows down. In this way, precise speed and position control can be achieved. Let's take an example. If we use a 4 MHz oscillator with a timer 2 prescaler value of 4 and PR2 equal to 120, then F command equals 1 MHz. The PWM period equals 0.484 milliseconds. As a result, the PWM frequency is approximately 2.066 kHz. This is how we can calculate the PWM frequency that will be used in our system. In this slide, you can see when programming the CCP module, we use the function setup CCP1 or setup CCP2. If the CCP PWM parameter is given, the module operates in PWM mode. If CCP off is given, the module is disabled. To set the duty cycle of the PWM signal, the function set PWM X duty is used. In the first line you can see. The letter X specifies which CCP module is being used. The value provided defines the duty cycle of the PWM signal. For example, after configuring timer 2 with the command in the first line, if we call the command in the second line, we get a 25% duty cycle. If we call the time, if we call the comment in the third line, we obtain 75% duty cycle. In this way, we can control the speed of the motor directly through software. Finally, here we see an example code that produces a PWM signal with 50% duty cycle at 2 kHz. We enable CCP1 in PWM mode using the code in the first line, configure timer 2, and then the code expressions in the last line generates a 50% duty cycle. This allows us to drive motor at full power. So, in summary, the PIC16F877 microcontroller can generate PWM signals using its CCP modules. PWM signals are the most commonly used method for controlling servo motors and DC motors in robotic manipulators. By adjusting the duty cycle, we can achieve precise control of motor speed and position, enabling robotic arms to perform the desired tasks accurately. That concludes.
Welcome and thank you for joining us today. My name is Mustafa Istanbulu and I am an assistant professor in this Department of Biomedical Engineering Department at Çukurova University. In this session, I will present on one of the fundamental components of modern robotics, robotic manipulators, focusing particularly on their basic principles and kinematics. My goal is not only to introduce the theoretical foundations, but also to demonstrate how these concepts work in practice. For that purpose, I have brought a small-scale robotic arm with me today, which we will use for a live demonstration later in this talk. Robotic manipulators lie at the very heart of the automation and robotics engineering. They are widely applied across many domains in industrial automation, where they perform welding, assembly, and material handling. In medical robotics also, where they enable surgical precision and rehabilitation therapies, and in research laboratories, where they provide repeatable and accurate movement for experimental setups. Despite the diversity of applications, the underlying concept is the same. A manipulator is essentially a mechanical arm designed to mimic the human arm. It consists of chain links connected by joints, which together allow complex movements in space. The final element of this chain is the end-effector, which interacts directly with the environment to accomplish a task. A robotic manipulator can be broken down into three essential components. First one is links. Links are rigid structures forming the skeleton of the arm. They are usually made of metal or lightweight materials such as composites or 3D printed plastic. The second one is joints, and they are connect the links and allow relative movement. They may be a rotation or translation. The last one is the end-effector. This is the functional tool of the manipulator, a gripper, a welding torch, and a scalpel, or even a specialized sensor depending on the application. In the small educational robotic arm I will be using today, the joints are actuated by SG90 micro servo motors. These are compact, lightweight motors that deliver surprisingly high torque for their size. Each SG90 servo can rotate approximately 180 degrees from about -90 degrees to +90 degrees, controlled entirely through the PWM, Pulse Width Modulation signals. The control principle is straightforward. A PWM pulse of about 1 millisecond drives the servo to its leftmost position. A pulse of 1.5 milliseconds centers it, and a pulse of around 2 milliseconds moves it to rightmost position. Because of this simple and reliable control scheme, SG-90 servos are extremely popular in robotics education, also hobby projects and maybe small robotic systems. They don't require additional motor controller or complex feedback circuitry, which makes them ideal for introducing students to real-world robotic actuation. By combining several SG-90 motor servos, this robotic arm achieves motion at its base, shoulder, elbow, and gripper, resulting in a total of 3 or 4 degrees of freedom. This setup is perfect for demonstrating the principles of manipulator kinematics. The concept of degrees of freedom, which we can say D or EF, is fundamental in robotics. It refers to the number of independent motions a manipulator can perform. For example, a 1 degree of freedom system might only move up and down. A 3 degree of freedom manipulator like the one I have here can rotate its base, lift or lower its shoulder, and bend its elbow. Advanced industrial robots often have 6 or more degrees of freedom, enabling them to reach almost any position and orientation in 3-dimensional space. In our educational arm, the base joint allows rotation left and right, the shoulder joint raises and lowers the arm, and the elbow joint bends to adjust reach, and the gripper opens and closes to grasp some objects. Even this relatively simple system is powerful enough to demonstrate the essential principles of robot kinematics. Kinematics in robotics addresses the motion without regard to forces or torques. It answers 2 critical questions. First one is the forward kinematics. If we know all the joint angles, where exactly is the end effector located in Cartesian space? Inverse kinematics, if we know desired position of the end effector, what should the joint angles be to reach that position? Forward kinematics is generally more straightforward. Using the Dennavit-Hartenberg convention, we define coordinate frames for each joint and express the transformation between them. By multiplying these transformation matrices, we can compute the position and orientation of the end effector. For example, rotating the base by 30 degrees, raising the shoulder by 45 degrees, and bending the elbow by 20 degrees will result in a specific position of gripper in 3D space. For inverse kinematics, however, it's more complex. In this case, we specify the target location of the end effector and must compute the necessary joint angles. In simple arms, this can be solved geometrically, but in more complex manipulators, the problem becomes nonlinear and may not have a unique solution. In such cases, numerical methods or some iterative algorithms are used to solve this problem. Industrial robotic systems rely heavily on real-time inverse kinematics solvers to perform precious tasks. Another concept to highlight its redundancy. If a manipulator has more degrees of freedom than required for a task, it's called redundant. The human arm is an excellent example. We can reach the same point with many different joint configurations. Redundancy provides flexibility and adaptability, but it also increases the complexity of the control problem. Now, let us put the theory into practice with this robot arm. First, I will rotate the base using its servo motor. This corresponds to the first angle, first joint angle, that's theta 1. Next, I will lift and lower the soldier by adjusting the theta 2. Then I bend the elbow, which gives us the angle theta 3. Finally, the gripper servo opens and closes to interact with objects. With these basic motions, we can perform simple tasks such as picking up a small object and placing it at a different location. What we just did is a real-world demonstration of kinematics. When we start from non-joint angles and observe the results and effector position, that is forward kinematics, as I said before. Conversely, when we start with the goal position and complete the joint angles required to achieve it, that is inverse kinematics. Even though this is a small-scale educational system, but the same principles apply to large industry robots again. The mathematics and algorithms are the same, only scaled up in the complexity and the precision. To conclude the topic, robotic manipulators are indispensable in modern robotics. Their ability to perform precious, repeatable, and complex movements is based on the principles of kinematics. Forward kinematics allows us to determine where the end-effector is given certain joint angles, while inverse kinematics allows us to compute the joint angles required to reach a target position. In our demonstration, we saw how even a simple robotic arm with SG90 servo motors can clearly illustrate these concepts by rotating joints and controlling servo angles through PWM signals. We directly connected mathematical theory to physical reality. In the upcoming session of this workshop, we will build upon this foundation. We will examine in detail how PWM signals and microcontrollers are used to control these SG90 servos in real time, and how such small-scale systems can teach us the principle underlying advanced robotic manipulators. This is the end of my presentation. I think 10 minutes later we will have hands-on session for control that robot.
Hello to everyone. My name is Erkan Demiş, and I'm going to talk about manipulator control in an experimental setting. As mentioned in the previous sections, our controller has two hardware PWM outputs. However, the manipulator used in this study includes 4 servo motors. Therefore, in order to control the motors of this manipulator, PWM signals will be generated through software rather than utilizing hardware PWM. In this work, the generation of software PWM signals will be achieved by jointly utilizing the 2 units of the microcontroller, namely the timer 1 module and the ADC module. Initially, a brief introduction of these 2 units will be provided, followed by a detailed explanation of the PWM signal generation process. The discussion will start focus on the PWM timer 1 module. The timer 1 module is a unit that can be used both as a timer and as a counter. Its features are listed below. It has a 16-bit timer and counter. It can read and perform read and write operations. Also, it has selectable internal or external clock source. Also, it has overflow interrupt when the timer 1 value rolls over from the 65,536. The timer 1 module contains 2 8-bit registers. With the timer 1 module, counting can be performed starting from any desired value within the range of 0 to 65,535. The timer 1 module can operate in 3 different modes. These modes are synchronous timer, synchronous counter, and asynchronous counter. In this study, timer 1 will be used as a synchronous timer. Now I'm going to talk about some specific functions of the timer 1 module. Setup timer 1 function. This command is a function used to configure the timer 1 settings. It is usage is given and this usage example is given. The parameter mode can be assigned one or more of the predefined constant listed below. The modes are timer 1 disables the timer 1. Timer 1 interval specifies that the timer 1 clock source will be the controller's operating frequency. Timer 1 external indicates that timer 1 clock source is external. Timer 1 external synchronous specifies that timer 1 will be synchronized with the external clock source. Timer 1 clock out enables the use of the timer 1 external oscillator. Setup timer 1 function. Timer 1 prescales constants include timer 1 d by 1, 2, 4, and 8, where the numeral at the end of each constant specifies the division factor. An example of this function is given, and the above example and the given example, it is specifies that timer 1 will be driven by an external source operating as a counter, and then the prescaler is set to 4. Set timer 1 function. This command is used to set the starting value of the timer 1 module. Since timer 1 is a 16-bit counter, the starting value must be between 0 to 65,535. This usage example is also given. In this example, the timer 1 starting value is set to 65,530. The calculation of the interrupt accuracy time. This formula contains T-command and multiplication of prescaler, multiplication of 65,536 minus timer 1 assigned value by using the set timer 1 function. T-command is equal to 1 division F command, and F command represents the controller oscillator frequency division by 4. Now I am going to introduce the ADC module functions of the microcontroller. Setup ADC function. This function is used to configure the mode of the analog digital conversion module. It specifies whether the ADC is enabled or disabled, whether the microcontroller's internal clock or an external clock will be used as the ADC clock, and if the internal clock is used, the division factor to be applied. Setup ADC ports function. Microcontrollers with an ADC module do not have dedicated input pins solely for analog digital conversion. General purpose I/O pins are used both for normal digital operations and for analog to digital conversion. However, these specific pins designated for analog digital conversion are fixed within the microcontroller. During program development, it is necessary to specify which pins will function as analog inputs for analog digital conversion and which will serve as a normal digital I/O pin. Therefore, this is achieved using the setup ADC ports function, which informs the compiler of the pins to be used as analog inputs. Additionally, this function is used to configure the positive and negative reference voltages input pins for the analog digital conversion. In this study, positive 5 volt and 0 volt will be used as where we reference positive and we reference negative respectively. Set ADC channel function. This function selects the channel for analog to digital conversion. When a command is used to convert an analog signal to a digital value, the microcontroller determines which input channels to convert using this function. Our microcontroller has 8 ADC channels, and these channels are given below. Now we can proceed the generation of 4 PWM signals. On the figure we can see our servo motor driven signal. In this process, the timer 1 module will be enable the generation of the PWM signals required for motor control with a period of 20 milliseconds or 50 hertz. This process will be repeated 200 times. Firstly, we use oscillator frequency as 60 MHz. Then we found f-command by using our oscillator frequency by divided 4. Then we calculate our interrupt occurrence time as 0.1 millisecond. Then this process will be repeated 200 times through coding to generate a signal with a duration of 20 milliseconds. Using 4 ADC pin, our microcontrollers, ADC conversion will perform for 4 potentiometers, which will then be used to control each motor individually. Our ADC settings are given. We are using 10-bit ADC conversion. By this, we are getting a value from ADC conversion between 0 to 1023. Then we are adding, we are adding 1000 to this value, and then divided by 100, we get the interval between 10 to 20. When we multiply these values to 0.1 milliseconds time of interrupt occurrence time value, we obtain a PWM signal between 1 to 2 milliseconds per cycle, which have a 5 volt value between these intervals based on potentiometer positions. Then we are going to use these signals, these 4 potentiometers, to control our 4 different servo motors position. We can see our CCSC compiler code for this project, this workshop. Firstly, we include the code our microcontrollers, then we specify our analog digital conversion bits. Then we can see the function for timer one interrupt. In this interrupt, we use set timer 1 value to get our 0.1 millisecond interrupt time. Then for 4 different motor, we have 4 different function block to control the PWM signals. You can see them on the code. Then in the while loop, we are using analog digital conversion functions to get the duty cycles between 1 milliseconds to 2 milliseconds. Also, we can see the 200 value to get the desired 20 millisecond PWM signals. Now, we first will perform the simulation application, and then we proceed to the experimental implementation on the hardware.
Arkadaşlar, şimdi de servo motor kontrolümüzle ilgili uygulamamıza geçelim. Bir robot kolumuz var. Bunun pik ve hazırladığımız koddaki gibi potansiyometreleri kullanarak 4 tane servo motorumuzu kontrol edelim. Şimdi ilk olarak devremize bakalım. Arkadaşlar, mikro işlemcimiz yerinde. Yine besleme devrelerini 2 tane ayrı güç kaynağı kullanacağız. Servo motorlarımızı kontrol etmek için soldaki güç kaynağımızı kullanacağız, enerji vermek için. Pik içinde sağdaki DC güç kaynağımızı kullanacağız. Bu DC güç kaynağımızdan pikin besleme devresini yaptık. Hatırlarsanız kod yazımında 16 MHz'lik bir kristal osilatörümüz vardı. Onu kullandık. Arkadaşlar, 4 tane potumuz var. Bizim PWM doluluk oranlarını ayarladığımız 4 ayrı motor için. Şemamızda da o şekildeydi. Bunların da ortadaki uçlarından mikro işlemcimizin analog dijital çevirim uçlarına giriş bağlantılarımızı şuradan sağladık. Daha sonra da 4 tane çıkışımız B0'dan B3 pinlerine kadar bir 330 ohmluk direnç üzerinden gördüğünüz gibi her motor için PWM uçlarına bağlantısını sağladık. Yani bizim şemamızda gördüğümüz bütün bağlantıları yaptık. Buradan bir tane motor üzerinden bu bağlantılara da bakalım. Bakın, bu ortadaki kırmızı kablo bizim için artı 5 volt kablosu olacak. Koyu kahverengi kablo bizim için referans ucu olacak güç kaynağımızın. Turuncu renge yakın olan kablo da PWM çıkış sinyallerimizi bağladığımız kablo olacak. Arkadaşlar, bakın burada 4 tane de potansiyometremiz var. Bunlardan birincisi birinci motor için çalışacak. Motorları da şöyle göstereyim. Burada en uç kısmına end-effector olarak isimlendireceğiz. Birazdan hareketini de göreceğiz zaten. Burada bir graspımız var. Bir tutucumuz var yani. Birinci motor. Bunun için kullanacağız. İkinci motoru şu motor olarak belirledim ben. Bu da bizim için aşağı yukarı yani end-effector'ımızın aşağı ve yukarı gitmesini sağlayacak. Üçüncü motor bizim öne ya da arkaya gitmesini sağlayacak end-effector'ımızın. Son motorda en dipten gövdenin sağa sola dönmesini sağlayacak. Normalde biz şu şekildeydi geldiğinde manipülatörümüz alt tarafına ben ahşap üzerine sabitledim ki hareket sırasında titremelerin az olması için, daha sabit durması için. Şimdi ilk olarak hazırladığımız PWM sinyallerine bakalım. Ben mikro işlemcinin bağlı güç kaynağını açıyorum. Bakın burada bir PWM sinyalimiz var. Bu birinci motorun çıkış ucu. Ben bunu en son noktasına getireyim ve her bir karenin değerini 1 milisaniye ayarladığımızda bakın bizim için olması gereken ilk değer neydi? 1 milisaniyeydi. Şu an bir kareyi dolduruyor. Ben potansiyometremi çevirdikçe bakın PWM sinyalimin doluluk oranı artıyor ve 2 kareyi dolduruyor şu anda. Yani maksimum konumda da 2 milisaniyelik bir doluluk oranına sahip olan bir PWM sinyalimiz var. Arkadaşlar şimdi de DC güç kaynağımızın diğerini açalım. Bakın robot kolumuz şimdi potansiyometreleri kullanarak aynı zamanda bu PWM sinyali de birinci motor için sadece birinci motorunkini bağlamıştık. Onu da değiştiğini göreceğiz. Bakın ilk potansiyometreyi çeviriyorum. Grasp tutucu ucumuz açılıp kapanıyor. Şimdi ikinci motoru çevirelim. Yukarı aşağı kısmına bakalım. Bakın yukarı çıkıyor. Aşağı iniyor. Şimdi öne arkaya kısmını çeviriyorum. Aşağı indi. Yukarı çıktı. Grasp'ımızı da ikisini birden kaldıralım. İki motoru birden kontrol ediyorum şu anda. Arkaya doğru çekelim. Aşağı indiriyorum. Şimdi de sağa sola çevirme kısmına bakalım. Bakın en temelden sağa sola yaklaşık 17 derecelik açılarla dönüşümüzü sağlıyoruz. Aşağı indirelim end-effector'ü. Yukarı kaldıralım, arkaya getirelim, öne getirelim. Son olarak da grasp'ı tekrardan açıp kapatalım. Sadece onun PWM sinyalini görüyorduk. Arkada PWM sinyalinin değiştiğini, yaklaşık 2 milisaniyelik bir doluluk oranına sahip olduğumuzda artık tamamen açıldığını, kapattığımızda da kapandığını görüyoruz. Aşağı indirelim. Öne getiriyorum. Aşağı indiriyorum. En aşağı konuma getirdim. Şimdi yukarı kaldıralım. Arkadaşlar gördüğünüz gibi 4 tane potansiyometre ile 4 farklı manipülatör üzerindeki servo motorumuzu kontrol ediyoruz. Bağlantılarımız aynı şemada gösterdiğimiz gibi PWM çıkışlarımız, yani 4 tane yazılımsal olarak hazırladığımız PWM çıkışlarını bizim manipülatörümüzün her bir motorunun PWM girişine bağladık. Besleme için, yalıtım sağlamak için özellikle 2 ayrı güç kaynağı kullanıyoruz. Onun dışında gördüğünüz gibi önemli olan burada yazılım hazırlamak, yani 4 farklı yazılımsal PWM sinyalini oluşturmak bizim için burada önemli olan nokta. Bunu hazırladıktan sonra kontrolünü gayet kolay bir şekilde bakın potansiyometrelerle manipülatörümüzün kontrolünü gerçekleştirebiliyoruz. Arkadaşlar şemamızın uygulanması da bu şekilde olacak.